Up to now, we have looked at situations with two choice variables and one constraint. But the theorem of Lagrange can be easily generalized to more variables and more constraints. So for example, here we would have n different choice variables, and then the vector x would just have n components, going from x1 via x2 and so on to xn, such that we have n different choice variables, or in the context of utility maximization, we would have n different goods. Then there can be also many constraints. Overall, there could be as many constraints as m, but the requirement is that this is strictly smaller than the number of choice variables. And we can write this down as separate equations here, where g of x is equal to c has to hold for I different equations with I going from 1 to m. So for example, one could have a budget constraint, but one could also have a time constraint, because we cannot go to the supermarket every 5 minutes. So we also want to take care of our time budget, and so on and so forth. And then the Lagrangian becomes a function of n choice variables and m Lagrange multipliers, which is then again the objective function here, plus now the sum over all I constraints, from I going from 1 to m, with m Lagrange multipliers, as we've written it down here. In this case, then, the necessary first order conditions at the optimum x bar would be that the derivative of the Lagrangian with respect to the j choice variables is equal to 0. That would give us j equations deriving from the first order conditions with respect to the optimal choices. But in addition, we would also have the derivatives of the Lagrangian with respect to the Lagrange multipliers, which are now m, and they have to be equal to 0, and this gives us m additional equations. So altogether, we would then have m plus n equations to solve for the m plus n unknowns, the choice variables, and the Lagrange multipliers. Now, this formulation here is a little bit cumbersome, bulky, but we can again use a more compact vector notation by following the conventions outlined in the book by Dixit, that a vector of partial derivatives of a column vector is a row vector, and then each constraint would have a row vector of partial derivatives g sub x of I, and these row vectors can then be stacked vertically to form a matrix m times n, of the dimension m times n, of the partial derivatives g sub x. And the multipliers themselves form a row vector lambda. We can then use the vector notation again, as I already said, to write down the Lagrangian function, which looks similar as before. But we just notice that now x is an n-dimensional vector. When we just say vector, we always refer to a column vector now. Lambda is an m-dimensional row vector. C is an m-dimensional column vector then again. F is a function that takes on a scalar value actually here. And G is a function that takes on m-dimensional vector values. So basically, this is the same formulation as we had before, but now with more dimensions than this two-dimensional vector that we had previously. The constraint qualification can now be written as the rank of the matrix G sub x, and this rank has to be m, which is the maximum possible. So that's the constraint qualification that should not fail. So at least for m different choice variables, the constraint must be binding. And then Lagrange's theorem would just be generalized that if a certain x bar maximizes the objective function and in addition it fulfills the constraint with no other constraints and with the constraint qualification being binding, then the derivative of the Lagrange function with respect to all the choice variables has to be equal to 0, and the derivative of the Lagrange function with respect to the Lagrange multipliers has to be equal to 0. And as stated before, this would provide us with a system of m plus n equations to solve for the m plus n unknowns, the choice variables, and the Lagrange multipliers. Another important generalization is to allow for non-negativity constraints. This could be relevant, for example, if the choice variables must not become negative for some reason. For example, you cannot consume a negative amount of a certain good. Now, this is not relevant if we want to consume positive amounts of this good anyway, then there would be no modification. But if we dislike a certain good, we might want to consume a negative amount if there is no restriction actually on the choice. But of course, in reality, we cannot consume a negative amount. So what we would do is to choose zero of the consumption of the good that we dislike. And to allow for these corner solutions, the necessary first order conditions have to be generalized and updated. And this is done here with a certain complementary slackness condition that states that one of these two conditions has to hold with a strict equality, actually. So what would we have here? We could have two situations. Either we like the good under consideration, then consumption of this good would be strictly positive. But if it is strictly positive, then the other one here has to hold with a strict equality. So that's the necessary first order condition that we already know from the standard theorem of Lagrange. So if we want to consume a certain good at the optimum, then the optimum requires that the derivative of the Lagrangian with respect to this good is equal to zero. However, then it could be that we dislike a certain good such that the derivative of the Lagrangian with respect to this good would be strictly negative. So we would derive, if we were forced to consume this good, a negative utility value from that. In this case, the derivative of the Lagrangian would be strictly negative, but then this other constraint has to hold with a strict equality. In this case, we would not consume anything of this good. And that means that the conditions hold with complementary slackness for each component pair. So that means whenever one condition holds with a strict inequality, the other has to hold with a strict equality. And basically the intuition for that is that the choice of zero of a certain good, which would be the case if the derivative of the Lagrange with respect to this good is negative, then we would actually have a satiation level that we have reached, and we would choose not to consume at all of this particular good. And for the other case, nothing would change as compared to the theorem of Lagrange that we have now. Our solution algorithm, the different steps as before, would be again to set up the Lagrangian, as we've discussed it already before, with the set dimensions of the different vectors and matrices, and the constraint qualification holds. And then we apply Lagrange's theorem, so we derive the derivative of the Lagrangian with respect to the choice variables x. That has to be non-positive. Then we have x, which has to be non-negative, and these component pairs hold with complementary slackness. So whenever we want to consume a positive amount of a certain good, then this Lagrangian has to hold with a strict inequality, so this derivative of the Lagrangian. And anytime we have that the derivative of the Lagrangian at the optimum is negative, then we have to consume a zero amount of the particular good. And then with respect to the Lagrange multiplier, nothing changes, so we take the derivative with respect to the Lagrange multiplier, and that has to be equal to zero. What changes, however, is that searching for the solution and solving the system of equations becomes much more cumbersome because we have to search through different combinations of restrictions to come up in the end with the solutions. We have to rule the combinations out that do not make any sense mathematically or economically. So we have to set here, we have to look at the situation when this one is negative and this one is equal to zero, and these are equal to zero, and then we have also to check for all of the situations where these are equal to zero and these are negative, equal to zero. And potentially this can lead to quite many combinations, 2 to the power of n, because we have n different choice variables that we have to look at. And of course, this could easily run into computational problems. The good thing is that in many applications, there are some shortcuts to finding a solution because we can rule out many of the combinations upfront because they do not make any economic or mathematical sense to begin with. Now there is a related but different generalization, and that is that the constraints might not hold with a strict equality. So we also want to generalize Lagrange's theorem to cope with inequality constraints, actually. And this is also of high economic relevance because often it's just not desirable to spend the whole budget or the whole income, so we don't go to the supermarket and spend everything we have, actually. It might be that we want to have something left in the end, that we don't want to buy everything. In this case, the constraint would not hold with a strict equality, but with an inequality, so we might be able to spend all that we have, but we do not need to spend everything that we have. We just cannot spend more than we have. So in this case, the constraint could hold with a strict inequality for some I. Now, what would happen in this situation and how would our solution algorithm look like? In this case, we would again set up the Lagrangian as before with the dimensions, and then Lagrange's theorem would tell us, or the generalized version, that x bar maximizes the objective function and satisfies the constraint in a way that the constraint might be not binding with the constraint qualification holding. And then if we don't have non-negativity constraints, then everything is as in the standard theorem of Lagrange with respect to the choice variable. So we would have that the Lagrangian, the derivative of the Lagrangian with respect to the choice variables has to be equal to 0. But now the derivative of the Lagrangian with respect to the Lagrange multipliers might not be equal to 0. It could be the case that a constraint is not binding, in which case the derivative of the Lagrangian with respect to the Lagrange multiplier would be strictly positive. Now this can, however, only happen, again with complementary slackness, if the corresponding Lagrangian multiplier is equal to 0. Intuitively, we would leave budget over only in case that we would not get any additional utility from spending the budget. So a relaxation of the budget constraint would not increase our objective function anymore, and this is exactly the case if the Lagrange multiplier is equal to 0. And then, of course, it could be that the Lagrangian multiplier is strictly positive, as before in most applications. In this case, the derivative with respect to the Lagrange multiplier of the Lagrangian function has to be equal to 0 with a strict equality, because then relaxing the budget constraint marginally would increase our utility, which means that we would spend more on a certain good. So in the end, the budget constraint would be binding. So again, this holds with complementary slackness. Whenever one of these equations holds with a strict inequality, the other has to hold with a strict equality. Finally, we can combine all the generalizations to the theorem of Karush-Kuhn-Tucker, actually. In this case, we would have non-negativity constraints on the variables and inequality constraints on the side constraints. And of course, we would have many different variables and constraints. So we would allow for, so the Lagrangian would look as before with the dimensions that we've already talked about. Then the Karush-Kuhn-Tucker theorem would tell us that if x bar maximizes the objective function and it satisfies the constraints, again with the constraint qualification holding, then we must have that both complementary slackness conditions from the inequality constraints that we had before and from the non-negativity constraints need to hold. So we would have both of the situations. Now, the choice variables could be equal to 0, so we would have corner solutions here. That would appear always when the derivative of the Lagrangian with respect to the choice variable is strictly negative. Then this one here would have to be strictly equal to 0, and vice versa. If this is strictly positive, then this one here has to be strictly negative. And we would also have the complementary slackness conditions with respect to the constraints. So whenever there is budget left with respect to a certain constraint, so the derivative with respect to the corresponding Lagrange multiplier is strictly positive, then the corresponding Lagrange multiplier itself must be strictly equal to 0 and vice versa. If the Lagrange multiplier is strictly positive for the corresponding constraint, then the derivative of the Lagrangian with respect to this Lagrangian multiplier, which is the specific constraint of this specific Lagrange multiplier, has to be equal to 0. Now, in this case, searching for solutions is again even more cumbersome than before because we would have to check for 2 to the power of m plus n different combinations of different conditions, the non-negativity constraints as well as the um, inequality constraints. But again, many applications that are of practical interest come with shortcuts to finding such a solution. Now we again look at an example where we apply the method of Karush-Kuhn-Tucker. We consider a situation where consumers choose between two goods x1 and 2, and now the quantities of the two goods have to be non-negative. The costs are again P1 is the price of good 1 and P2 the price of good 2. Then the consumer has income I, and now the budget constraint holds with an inequality constraint basically. So P1 times x1 plus P2 times x2 must not be strictly greater than I, but it can be strictly smaller than I. The utility function now is quasi-linear. Parameter a is greater than 0, and we have that the utility of the household, depending on x1 and x2, is then given by a times the logarithm of x1. So it's again, this is the logarithmic part of the utility function, that's concave. But then there is also a linear part of the utility function, where utility increases linearly with consumption of x2. And as we will see, this utility function actually implies that good 1 is a certain necessary good because the slope of the utility function for 0 consumption would be positive going to infinity. So if we start with a very small amount of consumption, move from 0 to a small amount, the slope is going to plus infinity. While the slope here is constant, so this is kind of not a necessary consumption good, and people would only consume this when they can ensure a certain consumption of x1 already. Now, in this case, again, we follow our algorithm. So we set up the Lagrangian first. That depends on consumption of x1, x2, and the Lagrange multiplier. Here we have the utility function, so the objective function from here. Then we have lambda times the constraint, where we have the right-hand side here and the left-hand side here with a negative sign. In step 2, we calculate again the necessary first order conditions for an optimum. So we take the derivative of the Lagrangian with respect to the choice of x1. We see here that's again a divided by x1 from here. This does not contain x1, so it drops out. And here only this term here contains x1, so it's minus lambda times p1. That's from here. Now this must be non-positive. It can be negative and it can be equal to 0, but it must not be positive. And with complementary slackness, it holds that x1 must be non-negative. So whenever this term here is strictly negative, this one here is equal to 0. And whenever this is strictly positive, this one here is equal to 0. Then the same holds true with respect to the choice of x2. Now here we see the derivative of the Lagrangian is this drops out, x2 does not appear. Here we have 1, and here we have, again, this drops out, and here we have minus lambda p2. So that's 1 minus lambda p2 is smaller or equal to 0, and x2 is greater or equal to 0. And then finally we have the derivative of the Lagrangian with respect to the budget, to the Lagrange multiplier. This gives the budget constraint, and this has to hold either with a strict inequality or with an equality, but it cannot be smaller than 0 because then the person would overspend. And again, with complementary slackness, this condition holds with the Lagrange multiplier being non-negative. So if this one here is strictly positive, the person leaves budget over, and therefore the Lagrange multiplier has to be equal to 0. So a relaxation of the budget constraint does not increase utility anymore. And by contrast, whenever this is strictly positive, this has to hold with equality. So in this case, the budget constraint would be binding. So now, in step 3, when we solve this, we have to consider that there are 2 to the power of 3, which is 8 possible patterns for equalities and inequalities here, basically. Because 3 is the 2 plus 1, so 2 is the number of choice variables and 1 is the number of constraints. So we would have to go one by one through them and say, well, let's start with this, where this is strictly positive, and this is equal to 0, and then consider all the combinations that are possible with the rest of the first order conditions, and so on and so forth, through all of these possible combinations. Now, of course, this is much more cumbersome than if we only have the standard Lagrangian situation. But now already we see that we can rule out that the budget constraint is slack here, because all the goods have positive marginal utilities. So from the utility function, good 1 increases utility and consumption of good 2 increases utility. So we know that in the end the budget constraint will never be slack, and therefore we have that lambda will be strictly positive, and this here will be strictly equal to 0. Formally, one can also see this, because if lambda were equal to 0, then we plug it in the first constraint. Then the first constraint would tell us that a divided by x1 has to be smaller or equal to 0. In this case, what we have is that this can never be fulfilled, because a and x have both to be positive, so this would not make sense. Now that we ruled out this, we have already ruled out basically 4 combinations, 4 possible solutions of the 8 that we have in general. Now it remains to check the other 4 possible solution combinations. Now first, let's assume that we have the solution where x1 and x2 are both equal to 0. Now this would not make sense. It can be ruled out, because in this case the budget constraint would not hold with equality. So if we consume nothing of both goods, the budget constraint cannot hold with equality, because we have all of our budget left. So this can also be ruled out. Then in case of 3, if we assume that x1 is equal to 0 and everything is spent on x2, then we can consume the budget divided by the price of good 2 in terms of x2. Then equation 7 from the previous slide would imply that lambda is 1 divided by p2, but then equation 6 would imply that p1 over p2 would be greater or equal to infinity, which cannot be the case. So this case can also be ruled out, and the intuitive explanation for that is actually that good 1 has this first marginal unit of consumption that implies infinite marginal utility. So actually here it would never make sense to consume nothing of good 1 and all of everything of good 2, everything of income, because good 1 actually comes with this that it is a necessary good in the sense that you cannot consume nothing of it. So we can also rule this solution out. Then there are 2 solutions remaining. One is that we do not consume anything of good 2 and spend everything on the consumption of good 1. So then we can consume the income divided by the price of good 1 in terms of consumption of good 1. Then equation 6 would imply that the Lagrange multiplier is a divided by I. And if we use this in equation 7, we would then have a restriction that income must not exceed the parameter a times price p2. Now this is just a restriction on the parameters, and it can be fulfilled. And if it is fulfilled, so that means we have one candidate solution for this situation. So when income is very low, below a certain threshold, then an individual, a rational individual in this case, would choose to consume nothing of good 2, but put all the income in the consumption of good 1. And that would make sense, because good 1 is a necessary good. If income is very low, good 1 has a very high marginal utility and much higher than consumption of good 2. So therefore, a rational individual would put everything of her money into the consumption of this good 1. So that could be, but there is also another possible solution where both consumption goods would be consumed at the positive amount. In this case, equations 6 and 7 would imply that a divided by p1 times x1 is equal to the Lagrange multiplier. That's equal to 1 over p2. And there we can then isolate x1, which would be a times p2 divided by p1. From the budget constraint, we could then derive that x2 must be equal to income divided by price of the good 2 minus the parameter a. And this then is consistent for a situation where income is higher than the threshold A times P2. Now, if this is fulfilled, this candidate solution applies. So if income is very high, the household would consume both goods. And that again makes sense because then the, um, the marginal utility of good 1 already becomes flatter because the utility function is concave, it's logarithmic. So then the household has enough income that this kind of luxury type of good, this good 2, consumption of this good becomes kind of worthwhile to consider. And we see here that actually we have now a solution for the whole parameter space. If income is very low, this solution applies, and if income is rather high, then this solution applies. Well, and in step 4, we can again discuss the solution, which we have already done. So from the 8 possible solutions, we were able to rule out 6, and we were able to reduce this to 2 possible solutions. And of course, it was much easier to analyze these 2 cases than the whole set of solutions. Now, these 2 solutions are mutually exclusive and exhaustive, meaning that the parameter space, we have a solution for the whole parameter space, that's the exhaustive here, and the solution is mutually exclusive, meaning that when the first solution holds, then the parameter space is such that the second does not apply, and vice versa. So we can split up the solution or the optimal choice x1 bar and x2 bar. The vector would be as we had it previously. So if income is low, below a times p2, and also if it's equal, then we would put all of consumption into good 1, all of income, and we would not consume of anything of good 2. And if income is higher than a times p2, then we would consume both goods, and we would have the demand functions that we've derived on the previous slide, basically. And again, the intuition, if income is low, then everything is spent on consumption of good x1 because it's a necessary good. Its marginal utility is infinity at a very low level of consumption. But if income is rather high and the basic needs are satisfied, then additional income will be spent on consumption of good 2.